The following video is of a compression test of various materials. The machine that I'll be using is called a hydraulic press. I will gradually increase the force applied to the samples until either failure or a predetermined value. On the left side of the machine there is a winch. The winch enabled me to lift the testing frame to the desired level. In order to increase the hydraulic pressure, I'll use a hydraulic pump, which is located at the right side of the machine. The samples I will be testing are mild steel round bar, cast iron square, and brass round bar. The reason I'm carrying out these compressive tests is to determine the amount of load each sample can withstand and to observe the failure mode. Design engineers must consider these properties when selecting a material for a particular application. The material must first be measured so that the original cross-sectional area can be calculated. I will be using vernier calipers to carry this out. Both cylindrical samples are 12.6 millimeters in diameter. So using the equation pi d squared over 4, we can work out the cross-sectional area. For the cast iron sample, we can simply multiply the width by the length to get the cross-sectional area. The height of the samples will also be measured and recorded. The table shown has been partially completed with the measurement information. Now that we have measured and calculated the original cross-sectional area of each sample, as well as the original height, we are ready to carry out the compression test for each sample. I will gradually increase the hydraulic pressure. This increase in hydraulic pressure will be translated to a force at the piston, which will be applied to the sample. As the mild steel specimen is compressed, it begins to bulge outwards on the sides and becomes barrel-shaped. With increasing load, the specimen is flattened out, increasing its cross-sectional area, which increases the resistance to further compression. This is a clear indication of malleability, which is expected as mild steel is known to be a highly malleable and ductile material. Grey cast iron can withstand a significant compressive load, as seen. When the test sample starts to fail, fractures start to appear at 45 degrees to the normal plane and propagate throughout the material. This fracture is a brittle type fracture. Cast iron performs well under compression, but poorly under tensile loads due to the structure of the material. The brass sample undergoes significant plastic deformation, work hardening the material. Eventually the material fails under compression in a sudden and brittle type failure mode at 45 degrees to the normal plane. The brass sample was not able to withstand as high compressive loads as the mild steel or the cast iron. A brass sample has fractured into two separate pieces at 45 degrees to the normal plane. The mild steel sample had a compressive load applied to it of 4,000 psi, as seen on the pressure gauge. We can convert this value to tons by using the chart attached. 1 metric ton is equivalent to 1,000 kilograms. We can use the equation force equals mass times acceleration to convert the mass to a force as shown. We follow the same steps to convert the cast iron PSI value to a force value as shown. Finally, we carry out the same calculations with the brass sample. Now that we have calculated the force applied to each of the samples in newtons, we can update the assessment task sheet with our force values. We will now measure the final length of the compressed samples with vernier calipers. The mild steel measures at 7.5 millimeters. The cast iron measures at 8 millimeters. And the brass sample measures at 9 millimeters in length. We can calculate the percentage reduction in length by taking the change in length and dividing it by its original length, using the formula shown on the screen. That completes the compression test of the 3 samples. The different mechanical properties observed influences the selection and application of these materials for various engineering components.